Hi there, and welcome to The Tired Scientist. I'm truly happy you've joined us. Tonight, we'll gently float through the skies above as we discover the hidden patterns behind our planet's weather, from light winds and booming thunder to soft snowflakes and golden afternoons that color the sky's ever-shifting mood. Think of this as a personal invitation to drift among the clouds, all while remaining cozy and warm wherever you may be. Just a kind heads up before we start. This video is made to help you relax and wind down, but fair warning, it may be just fascinating enough to keep your brain curious. And if you find yourself staring at the ceiling at 2 a.m. thinking about cumulonimbus clouds and the Coriolis force, well, at least you'll have learned something new. Before we begin, I'd love to know, where in the world are you joining us from? And what time is it for you right now? Whether you're watching late at night, early at sunrise, or somewhere in between, it's wonderful to have your company. If you enjoy calm, curiosity-driven adventures like this one, please consider liking the video and subscribing. It helps more people like you discover these gentle science journeys. Just one quick reminder, while we'll touch on topics like air pressure, temperature, and how weather may interact with your body, this video is meant for learning and relaxation only. It's not a replacement for medical advice or professional care. So if you have any health concerns, especially about heat or cold, it's always best to speak with a trusted healthcare provider. Now, if you'd like, gently close your eyes. Let your shoulders relax and take a long, deep breath. Tonight, we're setting out to uncover how weather really works, the science behind every drop of rain, arc of a rainbow, and distant thunder in the clouds. Let's begin by noticing something that's always around us but rarely gets our attention, unless it's causing trouble. The air. We live at the base of an invisible sea of gas, a moving, rippling ocean we call the atmosphere. Luckily, unlike the watery one, this ocean doesn't need a snorkel to breathe. Though, it can mess up your hair or blow papers away. This thin, vital blanket, about as thin, proportionally as apple skin, is where all weather unfolds. If you've ever looked out a plane window at cruising height, you've already passed through much of it. This atmosphere is layered like a cake, though not nearly as delicious. The lowest layer, where all our weather takes place, is called the troposphere. It's home to clouds, rain, and all kinds of windy antics. It rises about 7 miles high on average, stretching taller near the equator and dipping lower at the poles. Above the troposphere lies the stratosphere, home to the ozone layer, Earth's built-in pair of sunglasses, protecting us from the sun's more playful and potentially harmful rays. Continue your upward climb and you'll pass through the mesosphere, the zone where meteors light up in brilliant streaks across the night sky. Higher still is the thermosphere, a place of glowing auroras and drifting satellites, where temperatures can soar to thousands of degrees Fahrenheit, but it wouldn't feel hot, since the air is far too thin to actually transfer heat to your body. At the outer edge, the thermosphere fades into the exosphere, the atmosphere's faint final layer. Here, the air thins to near nothingness, and stray particles slowly slip off into the vastness of space. But for now, let's stay grounded in the troposphere, our atmospheric home base. The air down here is mostly nitrogen, making up roughly 78% of the mix. Oxygen accounts for about 21%. The remaining 1% is a cocktail of trace gases, like argon, carbon dioxide, and a touch of water vapor, varying with location. It may not sound glamorous, but this invisible blend is exactly what keeps life thriving on Earth. Let's dive into how air behaves, because this is where things begin to get fascinating and just a little chaotic. Air, like water, is a fluid. It moves, twists, rises, and responds to its environment. Most importantly, it reacts to shifts in temperature and pressure. Warm air rises because it's lighter and less dense, while cooler air sinks, being heavier. This simple rule, warm air going up, cold air coming down, is the very rhythm that drives all weather. When the sun shines on Earth, it doesn't heat things evenly. The equator basks in sunlight while the poles receive very little. Land absorbs heat faster than oceans. Mountains stay cooler than low valleys. These differences lead to uneven heating, creating pockets of warm and cool air. Since nature craves balance, the atmosphere constantly tries to even things out. Picture a sunlit patch of Earth. As it warms up, the air above starts to rise. As that air climbs higher, it cools. Cooler air can't hold as much moisture, so any water vapor it carries condenses into tiny droplets, forming clouds. Meanwhile, nearby cooler air flows in to fill the space left behind. This cycle is known as convection. It's the same principle that roasts your dinner or moves steam in boiling soup, just scaled up to sky-sized proportions. Now, onto pressure. Air has weight, not a lot, but enough that the entire column pressing down from above adds up to around 14 pounds per square inch at sea level. That's like having a small cat gently curled up on every inch of your skin. We call this atmospheric pressure. It shifts with altitude and changing weather. High-pressure systems are calm and steady, with air sinking and discouraging clouds. Low-pressure systems are more energetic, air rises, clouds form, and rain or storms often follow. When two areas have different pressures, air moves to even things out. This movement is wind. It's like the atmosphere tidying up, though in a very disorderly fashion. And because Earth spins fast, over 1,000 miles per hour at the equator, this air movement bends. That twist is called the Coriolis effect. It makes winds curve, to the right in the northern hemisphere, to the left in the southern. One of science's charming little tricks that feels almost like sorcery. But it's all just physics quietly doing its job. Add moisture, landscape features, and the time of day into the mix, and you've got a recipe for never-ending movement. The atmosphere is always in motion, always shifting, never exactly the same from one instant to the next. Even on a peaceful, sunny day, there are soft streams of air brushing by, minor shifts in moisture levels, and invisible temperature patterns gliding across the sky. It's not only a system full of life, it's bursting with it. What's truly remarkable is how this constantly swirling, changing engine needs no commands or controllers. It organizes itself, steered entirely by the laws of physics, gravity, and the ever-reliable rule of thermodynamics. Energy prefers to spread out. Heat naturally travels from warm regions to cooler ones, pressure seeks balance, and water forever cycles, evaporating, falling, and rising once more. The atmosphere desires equilibrium. It seldom finds it, but it never stops seeking. And that eternal search is why we experience weather, because Earth is a spinning globe wrapped in warm gases, dancing through sunlight and whirling in space. Every breeze, each cloud, every drop of rain, it's all part of the planet's ongoing pursuit of balance. So next time you spot clouds drifting across the blue or feel the wind stir your hair, remember, it's not just chance or chaos. These are movements in a grand, ancient system, an invisible, graceful ballet choreographed by sunlight and guided by gravity. And it all begins right here, in the very air that surrounds us. Though the sun is nearly 93 million miles away, it's still the ultimate conductor of Earth's weather. Without its heat, Earth would be a lifeless, frozen rock. No wind, no clouds, and certainly no weather apps trying and failing to predict sudden sock-drenching showers. The sun's rays are the main engine behind all weather. That energy reaches us as sunlight, or more precisely, electromagnetic radiation. But here's a surprise. The sun doesn't heat the air directly. Instead, it warms the land, the oceans, and everything lying on Earth's surface. These warm surfaces then pass their heat upward to the air above. So, it's not the sunshine itself that warms the sky, it's Earth's surface, glowing with absorbed energy, that does the job. Think of it like a stovetop. The burner heats the pot, and the pot warms the air rising off of it. Now, different parts of the planet absorb sunlight in varying amounts. Thanks to Earth's spherical shape and tilted axis, some regions bask in intense sunlight, while others receive just a faint glow. The equator, for instance, gets more direct sunshine than the poles. This uneven heating creates a lasting imbalance. Tropical zones warm rapidly, while polar regions stay icy cold. And where there's imbalance, nature tries to fix it. The outcome? Motion. Constant, breathtaking movement of air and heat. Near the equator, warm air rises, creating low pressure below. Cooler air from higher pressure areas rushes in to take its place. The rising air travels upward and moves toward the poles, gradually cooling. Farther north or south, It sinks and flows back toward the equator at lower levels. This large-scale circulation is called a convection cell. But since Earth is vast, round, and we humans love labels, we've mapped 3 major convection cells per hemisphere. Closest to the equator is the Hadley cell, followed by the Ferrel cell in the mid-latitudes, and finally, near the poles. Then we have the polar cell, completing the trio. These 3 circulation cells, Hadley, Ferrel, and polar, work together to transfer heat from the equator toward the poles, keeping the atmosphere in motion like a massive, unseen conveyor belt. Inside these cells, we find the world's major wind belts. Near the equator, for instance, blow the trade winds, steady easterly breezes that move from east to west. For centuries, sailors have relied on these dependable winds to cross oceans, sometimes even by accident. If you've ever wondered how explorers stumbled onto unknown continents, the trade winds likely had a hand in guiding their ships. Move a bit farther from the equator, and you'll reach the mid-latitudes. Here, we encounter the westerlies, winds that flow from west to east. These are the ones that steer weather systems across North America, Europe, and other temperate regions. Keep heading closer to the poles, and you'll meet the polar easterlies, cold, dry winds sweeping from east to west around the Arctic and Antarctic. Now, in theory, these wind patterns would travel in neat, straight lines, if the Earth weren't spinning. But our planet does rotate, and that leads us to the next twist in this weather story, the Coriolis effect. Because Earth spins on its axis, anything moving across its surface, including air, gets subtly nudged off course. Not because the atmosphere has stage fright, but because of physics. Here's a way to picture it. The Earth spins fastest at the equator and slower at the poles. So, when air travels from one latitude to another, it carries with it the speed of its starting point. This mismatch causes a curve. In the northern hemisphere, air veers to the right. In the southern hemisphere, it bends to the left. While the Coriolis effect isn't strong enough to make toilets spin, despite popular myth, it significantly shapes large-scale wind flows. It's the reason why cyclones swirl counterclockwise in the northern hemisphere and clockwise in the southern. It also helps wind patterns form organized, stable bands, instead of a messy tangle. Zooming out further, there's another major player in our global weather drama, the jet stream. Jet streams are slim rivers of fast-flowing air that wind their way through the upper atmosphere, usually found between distinct air masses. The most famous one is the polar jet stream, which separates cold polar air from warmer mid-latitude air. It flows about 6 to 9 miles above the ground and can race at speeds topping 200 miles per hour, faster than most sports cars, and thankfully without traffic. Jet streams arise from strong temperature differences high in the atmosphere and act like high-altitude highways, guiding weather systems across continents. When they dip or rise, they can trigger heat waves, cold snaps, or intensify storms, making meteorologists either excited or stressed. They even impact air travel. If your flight from west to east felt shorter than the return trip, you probably caught a boost from the jet stream, nature's version of a moving walkway, only much, much faster. But Earth isn't only spinning and radiating, it's also tilted. By about 23.5 degrees, to be exact. And this tilt is what gives us our seasons. As the planet orbits the sun, different regions receive varying amounts of sunlight throughout the year. When the northern hemisphere leans toward the sun, it's summertime. The days stretch longer, the sun climbs higher in the sky, and its rays strike more directly, bringing warmer temperatures. At the same time, the southern hemisphere is tilted away, experiencing winter. 6 months later, the situation flips. During the transitional periods, spring and autumn, both halves of the planet receive nearly equal sunlight. This gradual shifting in solar energy alters global temperature patterns, which in turn reshapes wind flows, influences the paths of storms, and changes how the oceans behave. Speaking of oceans, those vast, deep expanses of blue that cloak over 70% of the Earth's surface, they play an active role in shaping the weather. They soak up tremendous amounts of solar energy and store it like massive thermal batteries. Water doesn't heat up as quickly as land, but once it does, it holds onto that warmth far longer. This difference in how land and sea absorb and release heat is a major reason why coastal areas tend to have milder, more stable climates. The oceans are always in motion too. Giant currents like the Gulf Stream or the Kuroshio Current carry warm water across thousands of miles, helping to balance out temperature differences across the globe. And when ocean conditions change significantly, such as during El Niño or La Niña events, they can send ripples through the entire climate system, shifting rainfall patterns, triggering droughts, and swinging temperatures around the world. So, let's step back for a moment. Without ever leaving your comfy spot, you've now drifted through the intricate dance of Earth's weather engine. The sun warms our planet unevenly. That uneven heating makes air rise and fall. The Earth's spin causes that air to curve and swirl. Jet streams then sweep it across the skies like ribbons of wind. And the planet's tilt ensures that sunlight and weather are always on the move. The result is a world where every day is a little different from the last. A place where the breeze brushing your skin, the clouds overhead, and even the rain tapping your window are all pieces of a magnificent natural performance powered by sunlight and shaped by motion. It's a delicate choreography, one that's been playing out for billions of years. And at the heart of it all, from a light breeze to a mighty hurricane, is the sun's steady, far-off glow. Now, let's talk about moisture in the air, something you might only notice when your hair goes frizzy or your glasses fog up. Yet this invisible water vapor has a powerful influence on the weather. It forms clouds, brings rainfall and snow, and powers storms. It's also the source of some of the most stunning scenes in the sky. In short, moisture is the atmosphere's hidden force, present even when the sky appears completely clear. Let's begin with humidity, which simply means the amount of water vapor in the air. Water vapor is just water in gas form, and the air's ability to hold it depends on temperature. Warmer air holds more moisture, colder air holds less. That's why summer feels sticky and tropical, while winter feels crisp and dry. It's not just in your head, there truly is less water in cold air. When meteorologists talk about humidity, they usually mention two types: absolute humidity and relative humidity. Absolute humidity tells you the total water vapor present, like saying there are 12 grams per cubic meter. Relative humidity, though, is a bit more temperamental. Relative humidity is a percentage that compares the current amount of water vapor in the air to the maximum it could hold at that specific temperature. So, if the relative humidity hits 100%, the air is fully saturated, meaning it can't carry any more moisture. When that happens, condensation starts to occur, and you may begin to see things like dew, fog, or clouds forming in the air. You've likely felt this on a hot, sticky day, even if the air isn't technically saturated. High relative humidity can make everything feel heavier and more uncomfortable. That's because your sweat can't evaporate as easily in moisture-laden air, and evaporation is how your body naturally cools itself. In contrast, dry air helps sweat evaporate quickly, which can keep you cooler, though sometimes you might feel more like a desert creature than a tropical bird. Let's move on to clouds, those soft, billowy sky shapes that appear weightless but are anything but. Though they may look light and fluffy, clouds are made up of vast numbers of tiny water droplets or, if it's cold enough, ice crystals. Each droplet is incredibly small, so small that it takes roughly 1 million of them to make a single raindrop. And yet, an average cumulus cloud, the kind of big, puffy one you might have drawn in grade school, can weigh hundreds of thousands of pounds. Yes, a cloud can weigh as much as a jumbo jet, floating high above us as if gravity decided to take a short break. So how do these floating giants form? It all begins with evaporation. Sunlight warms water from oceans, lakes, rivers, and even moist ground, turning it into vapor. That water vapor rises through the atmosphere because warm air is lighter and more buoyant than cold air. As the vapor climbs, air pressure drops, causing the air to expand and cool. Cooler air can't hold as much moisture, so the excess vapor condenses into tiny droplets or ice crystals. These droplets cling to tiny particles like dust, salt, or pollen, which act as seeds, known scientifically as cloud condensation nuclei. These particles are essential. They give water something to hold on to and allow visible clouds to form. Different cloud types take shape depending on how the air rises and how moist it is. When the air lifts gently, you get stratus clouds, those flat, gray layers that often bring dull, overcast skies. When the air lifts quickly, it forms cumulus clouds, those big, fluffy cotton-like shapes. And when the atmosphere is both unstable and very moist, these cumulus clouds can rise even higher, growing into cumulonimbus clouds, the towering giants that power thunderstorms. There are many other clouds too. Cirrus clouds are high, wispy strands made of ice, often signaling incoming changes in weather. Lenticular clouds form over mountains and resemble flying saucers. Mammatus clouds hang like soft pouches and appear during intense storms. Then there's altocumulus castellanus, which looks like a row of little towers marching across the sky. The names may sound like they're straight out of a fantasy novel, but each belongs to the very real and poetic vocabulary of the sky. Once a cloud appears, it doesn't necessarily mean rain is coming. Before that happens, those droplets need to grow big enough to fall. Droplets begin to fall only when they overcome the pull of air resistance, and that happens through a process known as coalescence. This is when tiny droplets collide and combine, gradually forming larger ones. Once they reach a diameter of about 2 millimeters, they're heavy enough to fall as raindrops. In colder clouds, a different process takes place. Ice crystals form first, and moisture collects and freezes around them until they grow large enough to descend as snowflakes. Contrary to every cartoon depiction you've ever seen, raindrops aren't shaped like teardrops. As they fall, they take on a form more like a hamburger bun, rounded on top and flattened on the bottom due to air pressure. If a droplet gets too large, it may even split apart midair, breaking into smaller drops before reaching the ground. Of course, not all precipitation comes down as liquid. When the air from cloud to ground remains below freezing, we get snow. Snowflakes form when water vapor crystallizes directly into ice, skipping the liquid phase entirely. Their shape, whether needle-like, plate-like, or the classic six-pointed star, depends on the surrounding temperature and humidity. It's often said that no two snowflakes are exactly the same, and while that's technically true, it's more about statistical odds than poetic uniqueness. Considering the quintillions of snowflakes falling each winter, quite a few of them end up looking remarkably alike. When the air is warmer near the surface but the cloud is still cold, precipitation gets a little more complicated. Snow may melt partially into sleet, refreezing as it falls, or it might fall as freezing rain, which stays liquid until it hits a cold surface, then instantly ices over. This one is particularly sneaky, turning roads and sidewalks into slippery glass with barely any warning. Then there's hail, which isn't just frozen rain, it's something entirely different. Hail forms within strong thunderstorms that have intense updrafts. A small ice pellet begins high in the storm cloud, and powerful winds toss it around, allowing it to collect layers of supercooled water that freeze on contact. With each trip through the cloud, the hailstone grows bigger and heavier until it's too heavy to stay suspended and falls. Hailstones can range from the size of tiny peas to hefty grapefruits, though the really big ones are rare. Still, if someone says they saw hail the size of golf balls, they probably did. And it's best admired from a window, not the sidewalk. Water, of course, doesn't always fall from the sky to make its presence known. Sometimes it quietly settles as dew, those sparkling droplets you see on grass or windowsills in the early morning. Dew forms when the ground cools overnight by releasing heat, allowing nearby moisture in the air to condense. If temperatures drop below freezing, the dew transforms into frost, painting leaves and glass with delicate ice patterns. All of this, evaporation, condensation, precipitation, is part of the water cycle, nature's timeless recycling system. Water rises from oceans and lakes, forms clouds, falls again as rain or snow, and travels back through rivers to begin again. This cycle has persisted for billions of years, nourishing every form of life on Earth. And just before we move on, air doesn't need to be perfectly still for clouds or rain to form. In fact, fronts, or boundaries between different air masses, often trigger the most dramatic weather changes. When a warm, moist air mass encounters a cool, dry one, the warmer air is pushed upward. This upward motion sparks condensation and cloud formation, often bringing rainfall in its wake. That's why so many of the weather's sudden changes start with the arrival of a front. So next time you look up and spot a cloud drifting by, remember, it's not just a fluffy decoration. It's the visible edge of an unseen process, a graceful equilibrium of temperature, moisture, and movement unfolding silently in the sky. Every droplet in the breeze, every misty swirl, and every unexpected rain shower is a small part of this sweeping, skybound performance. And when the atmosphere decides to make a scene, thunderstorms are its fireworks. They rumble and flash, they pour with intensity, and sometimes even pelt rooftops with hail the size of walnuts. Yet for all their power, thunderstorms are made from simple ingredients: air, water, and a dramatic dash of electricity, like a stormy cocktail with a very loud sparkler on top. So how do these dramatic shows begin? At the center of every thunderstorm lies a basic principle: warm, moist air rising into cooler layers above. This rising motion is known as an updraft, and it's usually triggered by the heat of the sun warming the Earth's surface. Imagine a summer day where the ground has been soaking up sunshine for hours. A pocket of air near the surface warms up more than the air around it. Because warm air is lighter, it begins to rise. As it ascends, it encounters lower pressure, expands, and cools. If there's enough moisture in that rising air, it eventually reaches the dew point, the temperature at which water vapor condenses into liquid droplets. This transformation releases energy in the form of latent heat, which gives the air another lift, like fitting a balloon with boosters. The result? A growing cloud. At first, it might seem like a harmless cumulus cloud, soft and puffy. But given the right mix of moisture and atmospheric instability, it can expand into a massive, towering cumulonimbus cloud, a vertical powerhouse that can rise up to 10 miles high, surpassing even the height of Mount Everest. Inside this growing giant, the atmosphere is in chaos. The updraft pushes warm, moist air higher and higher, while downdrafts, cool air mixed with rain, plunge downward. This constant push and pull is what fuels the storm. When these opposing air currents become strong and organized, a thunderstorm officially begins. Meteorologists group thunderstorms into three distinct phases: the cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, rising warm air starts building the cloud, a process that's steady, gentle, and fairly quiet, much like slowly inflating a balloon. Then comes the mature stage where things get serious. The cloud grows upward, raindrops begin to fall, and flashes of lightning streak across the sky, accompanied by the crackle of thunder. This is the storm in full swing, with updrafts and downdrafts performing a complex aerial dance. Lastly comes the dissipating stage, where the downdraft dominates. The falling rain cools the surface and shuts off the storm's energy source, the rising warm air. Once the storm's fuel source, the rising warm air, is cut off, the thunderstorm begins to wind down. Without that steady lift, the storm's towering structure gradually collapses and fades away. But before we move on, we can't ignore the showstopper of any thunderstorm: lightning. It's nature's electrifying way of equalizing charge, and it does so with stunning style. Inside the churning storm, tiny ice crystals and water droplets are constantly bumping into one another, generating static electricity. Smaller, lighter ice particles usually gain positive charges and are carried to the cloud's upper regions by strong updrafts. Meanwhile, heavier hailstones and water droplets pick up negative charges and settle near the cloud's base. This separation sets up a massive voltage difference, sometimes reaching millions of volts, either within the cloud, between clouds, or between the cloud and the ground. Eventually, the electrical tension grows too strong for the air to insulate anymore. That's when a discharge occurs, and we see lightning. It all begins with what's called a stepped leader, a barely visible zigzag of negatively charged particles that snakes its way down from the cloud. As it nears the ground, the electric field becomes so strong that the Earth sends up a positive streamer to meet it. When the two connect, an intense surge of current rushes through the pathway, producing that brilliant flash of lightning we recognize. The air in this narrow channel is instantly heated to an astonishing 50,000 degrees Fahrenheit. That's about 5 times hotter than the sun's surface. This rapid heating causes the air to expand explosively, creating a shock wave. We hear that as thunder. Since light travels faster than sound, we always see the flash before we hear the boom. If you'd like to estimate how far a strike is from you, simply count the seconds between the flash and the thunder, then divide by 5. For instance, if you count 10 seconds, the lightning bolt was roughly 2 miles away. Lightning itself comes in several fascinating varieties. The most dramatic and hazardous is cloud-to-ground lightning, especially risky if you're holding something metallic in an open area. Then there's intra-cloud lightning, which flashes within a single cloud, and cloud-to-cloud lightning, where bolts leap between neighboring storm clouds, like skybound acrobats. Some rarer types are even more mysterious. Ball lightning, for example, appears as glowing orbs and is still not fully understood. Then there are sprites and blue jets, spectacular high-altitude electrical bursts that shoot upward into the mesosphere. Sprites often resemble red jellyfish and appear above massive storms. For years, pilots' reports of them were dismissed as illusions, but we now know they're very real and breathtaking to behold. While lightning is beautiful, it's also extremely powerful. A single bolt can unleash over 1 billion joules of energy, enough to momentarily power a small town. It can spark wildfires, damage structures, and, sadly, it can be deadly. That's why weather experts often say, when thunder roars, head indoors. It may not be a perfect rhyme, but it's solid advice. Thunderstorms don't just bring dramatic skies and lightning, they often come with hail as well. As explained earlier, hail forms in the strong rising currents inside a thunderstorm. Water droplets are pulled high into the cloud, where they freeze, then fall and get swept back up again, picking up more layers of water that freeze on contact. This loop continues, adding new icy coats each time, like building a snowball by rolling it again and again across a frozen field. Eventually, the growing hailstone becomes too heavy for the updraft to support, and it falls. Depending on the storm's strength, hail can range in size from tiny peas to large softballs. Thunderstorms also pack a punch in the form of strong winds. As cold downdrafts plunge through the cloud and strike the ground, they fan out horizontally, creating gusty winds known as downbursts. These can be quite forceful and are sometimes confused with tornadoes, though they behave very differently. And yes, tornadoes. Some thunderstorms, under just the right conditions, can spin up these intense funnels of wind. But not all storms are capable. Tornadoes tend to form within a special kind of thunderstorm called a supercell. A supercell is unique because it contains a rotating updraft, called a mesocyclone. This spin develops due to wind shear, which refers to changes in wind speed and direction at different altitudes. These changes create a horizontal tube of spinning air. When a strong updraft lifts this rotation upright, it starts to spin vertically, right within the storm. If conditions line up perfectly, that rotating column can intensify. A funnel cloud may form beneath the storm's base, and if it stretches down and makes contact with the ground, it becomes a tornado. Though these events are rare, they are among Earth's most destructive natural forces. Still, the majority of thunderstorms are much less extreme, brief outbursts of energy that deliver rain, wind, and the occasional bolt of lightning. Some storms form as part of multicell clusters, where several small storms are grouped together, or along advancing cold fronts, which lift warm moist air rapidly into the atmosphere. A particularly interesting feature linked to thunderstorms is the gust front, the forward edge of cool air rushing out from the storm's downdraft. As this cooler air spreads, it pushes warm air ahead of it upward, sometimes sparking the development of new storm cells. In this way, one thunderstorm can give rise to another, like an atmospheric game of tag. Despite their dramatic nature, thunderstorms are surprisingly common. At any given moment, about 2,000 of them are taking place somewhere around the globe. So while you're lying back, enjoying this calm narration, storms are flashing and growling above distant landscapes. They serve as a beautiful reminder that our atmosphere is constantly moving, pulsing with energy. Each thunderstorm is a brief, brilliant expression of nature's power, a ripple in the atmosphere's unending attempt to find harmony. And when the clouds flash and rumble, we're witnessing the sky's way of reaching for balance. It's more than just a rumble. Thunder is the atmosphere releasing pressure, an electric breath exhaled from the clouds. And when the sky truly wants to speak, when gentle breezes and scattered sprinkles no longer suffice, it unveils its most commanding performances: tornadoes and hurricanes. These giants of weather are the Earth's most powerful expressions, swirling with untamed force that can reshape entire landscapes and redraw the lines of coastlines. They're fierce, awe-inspiring, and often frightening. Yet, beneath their chaos lie the same foundational forces at work: air, moisture, pressure, and motion, only at their most extreme. Let's start with tornadoes. These are spinning columns of air that extend from a thunderstorm's base to the ground. They're usually brief, sometimes lasting mere minutes, but their strength can be staggering. Tornadoes hold the world record for the fastest surface winds ever observed, clocking in at over 300 miles per hour in rare cases. That's faster than a Formula One racer and considerably less forgiving. We still don't fully grasp every detail of how tornadoes form, but scientists have identified several critical components. First, you need an especially strong thunderstorm, typically a supercell, which we covered earlier. Supercells are unique because they contain a mesocyclone, a rotating column of air within the storm. This spin arises from wind shear, which occurs when winds at different altitudes blow in varying directions or at different speeds. Picture surface winds coming from the southeast while higher-level winds sweep in from the west at a faster clip. This contrast sets up a horizontal spinning motion in the lower atmosphere. If a thunderstorm develops above this rolling layer, its powerful updraft can tilt that spin into a vertical orientation, forming a rotating tower of air inside the storm. However, not every mesocyclone becomes a tornado. For that to happen, the rotation must tighten and descend, forming a visible funnel cloud. If that funnel makes contact with the ground, it becomes a tornado. This entire process is extremely sensitive, dependent on minute shifts in humidity, pressure, and terrain. Some storms tease a tornado for hours but never deliver. Others can suddenly produce a twister with minimal warning. Once formed, a tornado's forward speed can vary widely, from a slow crawl to more than 70 miles per hour. Most are relatively weak and short-lived, falling into categories EF0 or EF1 on the enhanced Fujita scale. But occasionally, nature spawns a monstrous EF4 or EF5, capable of leveling entire blocks and hurling vehicles like toys. The enhanced Fujita scale, ranging from 0 to 5, is based on the damage inflicted. An EF0 might snap small tree limbs and topple signs. An EF5, the most extreme, can rip homes from their foundations and leave behind wreckage that resembles a battlefield more than a weather pattern. Tornadoes are most frequent in the United States, especially in an area famously known as Tornado Alley. This region, stretching from Texas through Oklahoma, Kansas, Nebraska, and into parts of South Dakota, is commonly called Tornado Alley. Its landscape and weather patterns are ideal for tornadoes. Here, warm, humid air from the Gulf of Mexico collides with cold, dry air sweeping down from Canada and the Rockies, all beneath vast open skies. This perfect storm of conditions sets the stage for frequent tornado activity. But these swirling tempests aren't exclusive to the Great Plains. Tornadoes have been observed on every continent except Antarctica. Even over water, they appear as waterspouts, often seen off the coasts of Florida or across parts of the Mediterranean. Surprisingly, even Britain, despite its famously mild climate, experiences several tornadoes a year, though they tend to be gentler and far less destructive. Now let's look at the tornado's larger and more predictable relative, the hurricane. Known by different names around the globe, typhoons in the western Pacific, cyclones in the Indian Ocean, these vast, spiraling weather systems are much slower moving than tornadoes, but infinitely broader and longer-lived. While tornadoes are like sudden bursts of fury, hurricanes are giant engines of swirling atmospheric energy, capable of lasting for days or even weeks and spanning hundreds of miles. To create a hurricane, the Earth needs several ingredients. First, the ocean surface must be warm, at least 79 degrees Fahrenheit 26 degrees Celsius, and that warmth must reach down about 150 feet. This warm layer serves as the storm's energy source. Second, there must be an atmospheric disturbance, usually a cluster of thunderstorms. Third, the environment needs to have low vertical wind shear, which means that wind doesn't vary too dramatically in speed or direction with height. If wind shear is too strong, it disrupts the formation of the storm before it can organize. Once conditions align, the warm water evaporates, adding moisture to the air above. As this moist air rises, it cools and condenses, forming clouds and releasing latent heat, the same process we explored in thunderstorms. This extra heat causes surrounding air to rise faster, fueling a cycle of increasing motion. Thanks to the Coriolis effect, the air begins to spin, and a low-pressure center develops. This is known as a tropical depression. As the storm strengthens and draws in more moisture, it can become a tropical storm. Once its sustained winds hit 74 miles per hour, it's officially a hurricane. At the center lies the eye, a strangely quiet, clear spot of low pressure where winds calm and the sky may even show blue. Surrounding the eye is the eye wall, a ring of fierce thunderstorms with the storm's strongest winds and heaviest rains. Farther out lie rain bands, spiraling zones of showers and squalls stretching for miles. Hurricanes are categorized on the Saffir-Simpson hurricane wind scale, from Category 1 to Category 5, based on wind speed. A Category 1 storm, with winds from 74 to 95 miles per hour, can damage trees, roofs, and power lines. A Category 5 hurricane, packing winds over 157 miles per hour, can flatten communities and leave them unlivable for weeks. But it's not just the wind that makes hurricanes so deadly. Storm surge is another major hazard. This is a sudden rise in sea level caused by powerful winds pushing ocean water inland. It's often the most lethal aspect of a hurricane, particularly in flat coastal areas, where even a few feet of rising water can lead to catastrophe. When combined with relentless rainfall, storm surges can cause devastating floods, tearing through homes and infrastructure with terrifying force. And speaking of rain, hurricanes are prolific rainmakers. Some can release over 2 feet of rain in just a few days, overwhelming drainage systems and causing flash floods and landslides, sometimes far from the coast. Because hurricanes can be enormous and slow-moving, places not even near the eye of the storm may experience days of soaking rain and damaging winds, leaving widespread destruction in their wake. Oddly enough, these massive tempests play a key role in the planet's climate. Hurricanes act like giant atmospheric pumps, redistributing excess tropical heat toward the poles. It's violent and chaotic, yes, but it's also part of the atmosphere's ongoing attempt to balance itself, to shift energy away from the equator and even things out across the globe. Unlike tornadoes, hurricanes are generally more predictable. With modern satellite imagery and sophisticated computer models, meteorologists can often issue warnings several days in advance. These forecasts give people time to stock supplies, reinforce homes, or evacuate, significantly lowering the chances of casualties. But even with preparation, the enormous scale and intensity of a hurricane can make it extremely difficult to fully withstand or contain once it hits. Eventually, though, the storm runs out of fuel. As it moves over cooler waters or makes landfall, the hurricane is cut off from its heat source, the warm ocean surface. Without that steady supply of thermal energy, the storm begins to weaken, its winds slacken, and its rains lessen. What remains may be flooded streets and downed power lines, but from a meteorological standpoint, the hurricane has completed its journey, from a gentle tropical disturbance to a roaring atmospheric juggernaut, and finally to a dissipating storm fading into memory. Ultimately, both tornadoes and hurricanes are not random outbursts of nature. They are expressions of the fundamental forces behind all weather. They reflect a system out of balance, trying to redistribute heat, to normalize pressure, to find equilibrium in the ever-shifting air above us. In that way, they are not unnatural disasters but rather inevitable manifestations of Earth's dynamic energy engine. So, the next time you hear thunder echoing in the distance or watch spiraling storm clouds from a satellite feed, remember, these aren't just dramatic spectacles. They are the planet's loudest weather stories, written in air, water, and motion. They can frighten, fascinate, and amaze, but above all, they remind us how truly alive the sky really is. To restore atmospheric balance. The larger the pressure gap, the stronger the resulting winds. It's nature's attempt at organization, even if the outcome sometimes feels anything but organized. Imagine pressure differences as natural terrain. Air, like water, flows downhill from regions of high pressure into low pressure zones. But unlike a river, air doesn't follow a straight path. That's where the Earth's rotation, and our old friend the Coriolis effect, steps in once again. Because the Earth spins, moving air is deflected, to the right in the northern hemisphere, and to the left in the southern hemisphere. This deflection gives wind its curved trajectory, creating the large-scale circulation patterns we can see in satellite images and weather maps. Let's look at this from a global perspective. Near the equator, where solar radiation is strongest, the Earth's surface heats up dramatically. This causes warm air to rise, forming a low-pressure belt. That rising air spreads outward toward the poles at higher altitudes. Around 30 degrees north and south latitude, the air cools and sinks, forming high-pressure zones. From these zones, the air returns toward the equator along the surface, creating reliable east-to-west winds known as the trade winds. These steady winds were crucial for early explorers, who relied on them to navigate the oceans. Sometimes these voyages ended in triumph, other times in unexpected landfalls. In many ways, the age of exploration was powered as much by atmospheric physics as by human ambition. Between 30 degrees and 60 degrees latitude, the surface winds reverse direction, blowing from west to east. These are the westerlies, and they drive much of the day-to-day weather across North America and Europe. Closer to the poles, you'll find the polar easterlies, cold winds that flow from the east, pushing frigid Arctic or Antarctic air toward the middle latitudes. Altogether, this creates a planet-spanning circulation system, a complex ballet of wind belts and jet streams. But wind isn't only about vast global patterns. It's also a profoundly local phenomenon. Some of the most interesting and memorable winds occur on a small scale, shaped by landforms, bodies of water, and daily temperature changes. Take sea breezes, for example. On warm afternoons, land heats up faster than water, causing the air above land to rise and form a low-pressure zone. Cooler, denser air over the ocean rushes in to replace it, creating a breeze that flows from sea to land. After sunset, the land cools more rapidly than the ocean, reversing the process and sending air back toward the water. This gentle, back-and-forth rhythm is one of the simplest wind cycles in nature, and also one of the most calming. In mountainous terrain, winds get even more dramatic. As the sun warms mountain slopes, air near the surface rises, pulling cooler air up from the valley. This is called an anabatic wind. At night, cold, dense air flows downhill, creating a katabatic wind. These daily cycles are part of life for those in mountain towns. Some katabatic winds are so iconic they've earned names of their own. The Mistral in southern France, for example, is a brisk, dry wind rushing down the Rhône Valley. It can howl at over 50 miles per hour and is so influential that local homes are built with small, protected windows turned away from its wrath. In California, the Santa Ana winds blow from desert to coast during certain months. These hot, dry gusts can worsen wildfires, drying brush and spreading flames rapidly. Their arrival is met with a familiar mix of fascination and fear, a vivid reminder of the wind's raw, unpredictable power, yet sometimes perilous force. One of the most remarkable wind patterns on Earth is the Chinook wind, often nicknamed the Snow Eater. Chinooks sweep down the eastern slopes of the Rocky Mountains, bringing sudden warmth and dryness as they descend into the plains. These winds can trigger an astonishing temperature jump, sometimes increasing by 40 degrees Fahrenheit or more in under an hour. Picture heading out on a frigid winter morning and removing your coat by midday. It's as if the atmosphere flipped on a colossal hairdryer. But wind doesn't always arrive with warning. Some gusts strike abruptly and powerfully. Microbursts, for example, are short-lived but intense downdrafts that develop during thunderstorms. These descending air columns slam into the ground and fan outward, damaging everything in their path. The destruction caused by a microburst can resemble that of a tornado, toppling trees, tearing at rooftops, and endangering aircraft during takeoff or landing. Then there are the playful but deceptive dust devils, miniature whirlwinds that swirl up on hot, dry afternoons when the ground heats unevenly. They're not true tornadoes, even if they look like pint-sized versions. Dust devils are typically harmless, just slender columns of spinning air and dirt, maybe a few feet wide and several dozen feet tall. They're common in desert regions and are more likely to star in a viral video than cause any real harm. On the larger end of the wind spectrum, we encounter gales and cyclones. A gale involves sustained winds of over 39 miles per hour, strong enough to sway trees and make simply walking a challenge. Cyclones, depending on their strength and location, can unleash hurricane-force winds, relentless rain, and dangerous storm surges that inundate coastlines. Though their names vary across regions, their impact is universally intense. Yet not all winds are wild or attention-grabbing. Some move quietly through the background, shaping weather and life in subtle but significant ways. High in the atmosphere, above the clouds, are the jet streams, narrow bands of extremely fast-moving air. Found near the tropopause, these aerial highways zoom along at speeds between 100 and 200 miles per hour, usually from west to east, steering storms and even influencing your flight arrival time. Jet streams form where warm and cold air masses meet, such as along the boundary between the polar air and the mid-latitudes. Their paths bend and twist like high-altitude rivers, shifting with the seasons. When a jet stream dips southward or meanders, it can trap weather systems in place, leading to long heat waves, flooding rains, or extended cold spells. Despite its invisibility, wind is a master sculptor. It moves moisture, spreads seeds and pollen, and slowly wears down mountains into sand. It molds sand dunes in arid deserts and shapes icy drifts in polar regions. It propels sailing ships across oceans and spins wind turbines across flatlands. Wind is both a whispering breeze and a powerful agent of transformation. Across history, humanity has depended on wind. Ancient sailors read its cues to cross oceans. Farmers still look to the skies for wind shifts before storms. And today, we capture its force to generate clean energy. No smoke, no fire, just spinning blades turning air into electricity. Yet it plays a crucial role in regulating temperature. Wind moves warm air away from overheated areas and delivers cooler air to places that need relief. On a sweltering afternoon, a breeze can feel like a lifesaver. On a bitter winter morning, it can slice through layers of clothing with a sting. This is where the concept of wind chill comes into play. It describes how the wind increases heat loss from your skin, making it feel colder than the actual temperature. While wind chill doesn't lower the temperature itself, it makes a huge difference in how you experience it. Despite how random it may seem, wind is not unruly. It operates under exact physical principles. It follows pressure gradients, shaped by terrain, temperature differences, and the Earth's rotation. Whether it's the soft flutter of leaves or the fierce gust of a snowstorm, wind is the Earth's way of expressing itself, an ever-present atmospheric voice. So the next time you see the treetops swaying or feel a current brush past your cheek, pause and notice this invisible artist at work. It's always in motion, quietly shaping the space around you. Though you can't see it, wind is a powerful reminder that our sky is very much alive. When winter settles in, it doesn't arrive with subtlety, it sweeps in with force. Trees shed their final leaves and stand in quiet stillness, ponds harden into icy mirrors, and the air takes on a sharp, crisp edge that cuts right through layers. Snow begins to blanket rooftops and roads, muffling sound and turning the world into a tranquil white wonderland. Yet beneath this serene exterior lies a rich scientific story. Snow, sleet, ice, and freezing rain are more than just seasonal nuisances, they're the visible signs of the atmosphere's coldest and most intricate behavior. Let's begin with snow, the poster child of winter. Each snowflake starts out high above the ground, forming around a minuscule dust particle. Water vapor in the cold air condenses onto this speck and immediately freezes into a tiny ice crystal. As the flake drifts downward through the cloud, more vapor sticks to it and freezes, causing it to grow. The constantly changing conditions of temperature and humidity shape each flake uniquely, which is why no two snowflakes are alike, or at least, the odds of finding identical ones are astronomically low. Most snowflakes take on a six-sided or hexagonal structure due to the molecular bonds in water. Water molecules naturally form at specific angles, leading to symmetrical and often stunning patterns. Some flakes resemble plates, others needles or stars, and under a microscope, they display remarkable geometric beauty, crafted solely by cold air and moisture. Though snow is light, it accumulates quickly. A single cubic foot of fluffy snow can weigh 5 to 15 pounds, depending on how much water it contains. Multiply that by millions of flakes, and it's easy to see how a gentle snowstorm can become a heavy load on rooftops and trees. Wet snow, being denser, carries more weight and poses more risk. Not all winter precipitation is as graceful. Sleet forms when snowflakes melt slightly as they fall through a warmer layer, then refreeze into ice pellets before reaching the ground. These pellets bounce on impact and create a crunchy but passable surface. Freezing rain, however, is a more deceptive form of winter weather. Like sleet, it begins as snow aloft. It turns entirely into rain as it descends through a warm air layer. But then, just before reaching the ground, it passes through a thin pocket of freezing air. The temperature near the surface is below zero, yet the rain doesn't solidify in midair. It doesn't have time. Instead, it stays in a liquid state, what scientists call supercooled. The moment it touches anything solid, whether it's pavement, a parked car, or a bare tree branch, it instantly freezes, creating a slick, invisible layer of ice. This glaze ice sparkles in the sun but can be deceptively dangerous. It transforms every tree limb into a crystal sculpture and every step into a potential flip. Unlike snow, which can be scooped or plowed, this kind of ice bonds tightly to surfaces, making travel extremely risky. Freezing rain is a major winter culprit behind widespread power outages. That thin coat of ice might be light at first, but as it thickens, the weight becomes too much for tree branches and power lines to bear, often leading to snapping and falling debris. Then there's frost, the intricate lace of winter mornings. Frost appears on cold, still nights when surfaces cool below both the dew point and freezing temperature. In this case, water vapor in the air bypasses the liquid phase and transitions straight into ice crystals, a process known as deposition. The result is a white, shimmering coating on windows, grass, or rooftops, shaped like feathers, ferns, or spiderwebs. A more extreme version of frost is hoarfrost, which forms under a perfect set of conditions: very humid air, calm winds, and very cold temperatures under clear skies. The ice crystals grow into long, spiky structures that resemble needles or coral, covering entire surfaces with a dreamlike sparkle. Hoarfrost doesn't fall like snow. It forms directly where it's seen, turning the environment into a scene from a fantasy novel. Sometimes winter also brings ice fog, a surreal mist made of countless microscopic ice crystals. This happens when moisture in extremely cold air freezes near the surface, filling the lower atmosphere with a shimmering haze. It's common in Arctic regions like Alaska and northern Canada, where temperatures drop well below -20 degrees Fahrenheit. Ice fog sparkles in streetlight beams and creates dangerously low visibility, much like regular fog, but with a diamond-dusted finish. And we can't overlook wind's role in winter's bite. Cold air already chills, but wind chill makes it feel much colder. This isn't just a sensation, it's a scientifically calculated measure of how fast heat leaves your skin due to wind. Your body warms the air directly next to your skin, forming a small insulating layer. Wind blows that layer away, forcing your body to keep reheating itself. The stronger the wind, the more intense the heat loss, and the colder it feels. For instance, if it's 20 degrees Fahrenheit outside with a 15 miles per hour wind, it may feel like just 5 degrees Fahrenheit. While the air temperature doesn't actually drop, wind chill increases the risk of frostbite and hypothermia. Now, meet winter's heavy hitters, blizzards. These aren't just heavy snowfalls, they're defined by wind and poor visibility. By meteorological definition, a blizzard must include sustained or frequent wind gusts of 35 miles per hour or more, visibility reduced to a quarter mile or less, and those conditions must persist for 3 hours or longer. Interestingly, a blizzard can strike without fresh snow if loose snow is whipped around by howling winds. These storms can shut down entire cities, can leave travelers stranded and create complete whiteouts, making even nearby destinations nearly impossible to reach. Despite their intensity, blizzards start with surprisingly familiar ingredients: humid air, chilly temperatures, and unstable atmospheric conditions. On the other hand, snow squalls are short but fierce. These sudden bursts of snow and wind can appear out of nowhere, drastically cutting visibility in a matter of seconds. Though they rarely last longer than an hour, their rapid onset and intensity can lead to abrupt temperature drops and hazardous road conditions. If you've ever been driving in sunshine only to find yourself surrounded by blinding snow moments later, you've likely driven straight into a snow squall. Though winter weather poses many challenges, it also plays a crucial role in maintaining the Earth's balance. Snowpacks in mountainous regions are natural reservoirs, storing water through the winter and releasing it slowly as they melt in spring. This provides fresh water for ecosystems, agriculture, and human use. Ice and snow also help moderate the planet's climate by reflecting sunlight away from the Earth, a process known as the albedo effect. Even the frost blanketing soil serves a purpose. It acts like a winter blanket, keeping the Earth beneath from freezing too deeply and protecting plant roots from extreme conditions. So, when you see your breath-forming mist in the air or watch a delicate snowflake land on your sleeve, you're not just observing winter, you're witnessing a masterpiece of atmospheric physics. Each snow-covered field, each icy branch, is crafted through an intricate blend of temperature, motion, moisture, and timing. There's an elegance in every snowstorm, a silent choreography shaped by invisible forces. Yet not all weather announces itself with sound and fury. Some of it sneaks in, soft and quiet, no thunderclaps, no heavy snowfall, just a gentle thickening of the air. A gray curtain drapes over the landscape, muffling noise and distorting shapes. This is fog, weather's quiet enigma. It doesn't shout, it whispers. It turns ordinary scenes into soft-edged mysteries. And though it seems simple, fog is layered with subtle science. At its essence, fog is just a low-lying cloud. It forms when water vapor condenses into countless tiny droplets that remain suspended close to the surface. These droplets are too small to fall as rain, so they simply float, scattering light and blurring everything around them. The result? A hushed world where distance vanishes and the air feels thick with secrets. Fog comes in several forms, each shaped by unique conditions: temperature shifts, moisture, terrain, and time. One of the most common is radiation fog, which develops on calm, clear nights. As the ground loses heat, it cools the air immediately above it. If that air is moist enough and cools to its dew point, condensation begins and fog rolls in. This type of fog often forms in valleys and low areas and typically appears just before dawn. It's fragile, easily dispersed by a breeze, and it lifts as the morning sun warms the earth, peeling back like a theater curtain rising at showtime. Another type is advection fog, formed not by nighttime cooling but by warm, humid air moving over colder ground or water. Picture a warm sea breeze gliding over a chilly coastline. The cold surface cools the air above it, and if it hits the dew point, a thick fog emerges. Advection fog can span great distances and persist all day, especially near oceans. It's the mist you picture in old maritime tales, where ships vanish into gray horizons. When damp air is pushed upward along a slope, it begins to cool as it gains elevation. The higher it climbs, the thinner the air becomes, causing the temperature to drop. If the cooling reaches the dew point, fog develops. Unlike radiation fog, upslope fog can form during any part of the day and tends to stick around until wind direction changes, often making it more persistent. Now let's meet a less common type: evaporation fog, sometimes called steam fog. This variety forms when cold air flows over warmer water. You might notice it rising off lakes, rivers, or even a backyard hot tub on a chilly morning. The warm water evaporates into the cold air hovering just above it, increasing moisture levels rapidly. That sharp contrast between the warm, rising vapor and the cool air triggers instant condensation. The result is curling wisps of fog drifting upward like steam from a boiling pot, a mesmerizing, fleeting dance of warmth meeting chill. Another eye-catching form is freezing fog, one of the more dangerous types. In this scenario, the air temperature is below freezing, but the tiny fog droplets remain liquid, a state known as supercooling. These delicate droplets can exist in liquid form even when it's well below 32 degrees Fahrenheit. As soon as they touch a surface, be it a branch, side mirror, or telephone wire, they freeze on contact. What forms is rime ice, a coarse, opaque layer of frost that can transform a landscape into a winter wonderland. Unlike frost, which crystallizes directly from vapor, rime builds from actual liquid droplets freezing in place. It can coat things rapidly and pose real hazards, especially to drivers in airplanes. Yet it also has an artistic side, turning ordinary scenes into icy sculptures shaped by wind and temperature. Not all fogs are created alike. Mist, for example, is nearly the same as fog but less thick. The key distinction lies in how far you can see. If visibility remains greater than 1 kilometer, just over half a mile, it's mist. Anything less is officially considered fog. Mist feels softer and more suggestive than fog, but it's made of the same minuscule droplets and develops under nearly identical conditions. Then there's haze, which from afar can resemble fog but comes from a different source. Instead of water droplets, haze results from dry particles in the air, such as dust, smoke, or pollution. These particles scatter light differently than fog, giving the sky a pale, flat appearance. Haze doesn't have the dampness of fog and doesn't need the same temperature or moisture levels to form. However, it can still affect visibility, mood, and respiratory health. Fog has an intriguing effect on sound as well. In thick fog, sound waves behave unpredictably. They scatter and sometimes seem muffled, making noises feel closer or farther than they truly are. A train whistle might feel distant and faint 1 second, then shockingly loud the next. This warping of sound contributes to fog's eerie atmosphere. It doesn't just obscure sight, it disorients your hearing too. And then there's how fog plays with light. When headlights or flashlights hit dense fog, the light bounces off the droplets and reflects straight back, causing intense glare that can make it even harder to see. This explains why driving in fog can be so challenging. Your high beams end up lighting up the fog itself instead of the road. That's why vehicles come equipped with fog lights placed lower on the front bumper. These lights are aimed beneath the densest layer of fog, helping drivers see just far enough ahead to stay on course. But fog isn't just a weather nuisance, it carries emotional and cultural significance. It appears in poetry, movies, thrillers, and fairy tales, evoking feelings that range from serene to unsettling. It's not just a condition, it's a backdrop, a tone setter, and a powerful symbol all at once. Fog invites you to slow down, to be more observant, to listen more intently. It gently encourages mindfulness. Yet behind that calm, dreamy presence lies real atmospheric science. Fog is governed by dew points, temperature shifts, and airflow. It may seem like the most passive form of weather, but there's an intricate, active process behind it. So, the next time you wake up and see the world veiled in fog, step outside. Feel the moisture clinging softly to your skin. Notice the way visibility fades and reappears as if the landscape is breathing. Realize that you're not beneath a cloud, you're inside one. It's a rare moment where weather surrounds you so intimately, blurring the line between sky and earth. And while fog embraces gently, not all weather arrives so subtly. Some systems creep in without sound or spectacle, gradually changing the atmosphere until everything feels sluggish and overheated. This brings us into the realm of heat waves and droughts, where the air grows heavy, the ground splits open, and even the breeze carries heat instead of relief. Let's begin with heat waves, those prolonged episodes of extreme warmth that seem to roast everything in their path. A single hot afternoon isn't a heat wave. This term refers to sustained periods, often several days long, during which temperatures soar well above average for that region and season. High humidity often accompanies the heat, making the air feel even more oppressive. Definitions vary by location. What's considered dangerously hot in Northern Europe may be just another summer day in the American Southwest. Still, a heat wave typically lasts 3 or more consecutive days, with daily highs far above the norm. Some heat waves linger for a week or longer, especially when a stubborn high-pressure system settles in and refuses to budge. These high-pressure zones, sometimes called ridges, act like domes pressing down on the atmosphere. From a meteorological perspective, the air within these systems is descending. As it sinks, it compresses and warms up, while also suppressing cloud development. With few clouds to block sunlight and no rising air to form rain, the sun's energy slams straight into the ground, and it accumulates. In certain areas, heat waves are worsened by local features. Urban environments, for example, are prone to the urban heat island effect. Concrete, pavement, and buildings trap and radiate heat, making cities significantly hotter than nearby rural zones. Add human activity and limited vegetation, and urban centers become heat magnets. And keeps nighttime temperatures high, preventing proper cooling. That's why urban nights often remain hot, while nearby rural areas cool more comfortably. Natural surfaces like grass, soil, and trees release stored heat efficiently, whereas buildings and pavement trap warmth like a heated brick. Another major player in how we feel heat is humidity. When the air is thick with moisture, our bodies struggle to cool down. Sweating, which is the body's main cooling method, works by evaporating moisture off the skin, carrying heat with it. But when humidity is high, that sweat doesn't evaporate as easily, making us feel hotter than the thermometer suggests. This is where the concept of the heat index comes into play. Much like the wintertime wind chill, the heat index reflects how hot it feels when humidity is considered. For instance, if the air temperature is 95 degrees Fahrenheit with 55% humidity, your body actually feels closer to 110 degrees Fahrenheit. That kind of oppressive heat can soften asphalt, fry tempers, and make wearing jeans feel like punishment. But beyond discomfort, excessive heat can seriously threaten human health. Prolonged exposure can lead to heat exhaustion or heat stroke, both of which are medical emergencies. The elderly, young children, and people with existing health problems are particularly vulnerable. Common warning signs include faintness, rapid pulse, nausea, and disorientation. During extreme heat events, hospitals often see a spike in emergency cases. That's why public cooling shelters, shaded green spaces, and access to fans or air-conditioned rooms can genuinely save lives. Now, let's shift to another form of heat-related stress, droughts. Unlike heat waves that hit quickly and visibly, droughts sneak in and settle silently. A drought is a prolonged stretch with far less rainfall than usual, gradually leading to water scarcity. There are no loud alarms, just clouds that never open. Droughts can stretch across weeks, months, or even span years. Some unfold slowly after a dry season or two, others begin abruptly when expected rains fail to arrive. While the exact outcomes vary by region, the impacts are always profound. Rivers dwindle, reservoirs shrink, and parched land cracks underfoot. In agriculture-heavy regions, crop stress leads to failed harvests, dead vegetation, and rising food insecurity. In the worst scenarios, droughts result in famines, forest loss, and even mass relocation as people leave uninhabitable areas in search of water and food. Experts classify droughts in multiple ways. Meteorological drought simply means less rain than normal. Agricultural drought refers to dry soil and struggling crops. Hydrological drought involves reduced water in lakes, rivers, or aquifers, and socioeconomic drought begins when these issues ripple into economies, restricting water use, shrinking yields, and inflating food prices. Several global factors can influence drought, such as weather cycles like El Niño and La Niña, which shift rainfall patterns. El Niño often brings dryness to areas like Australia and Southeast Asia, while La Niña alters jet streams and can reduce rain in the U.S. Southwest. Other contributors include persistent high-pressure systems, shifting ocean currents, and longer-term climate change. As global temperatures rise, so do evaporation rates, which draw water from soil and vegetation even faster. Rainfall, when it does arrive, may not be enough to replenish the loss. Worse still, Heavy rain after drought often runs off hardened ground, causing flash floods instead of relief. Heat waves and droughts often feed each other. Dry land evaporates less, reinforcing the cycle, which allows the heat to intensify even more. With no moisture to soak up the sun's energy, that energy goes straight into raising the temperature of the land and the air. It creates a self-reinforcing cycle, trapping regions in extended periods of scorching, bone-dry conditions. Though difficult, both heat waves and droughts are not new. They've been part of Earth's climate rhythm for millions of years. However, in recent times, scientists have observed that these events are becoming more frequent and more intense in many regions. Much of this increase is linked to climate change. A warmer atmosphere stores more thermal energy, which fuels more extreme weather, making heat and drought events more severe and more likely. To cope with these rising challenges, adaptation strategies are gaining urgency. Cities are turning to green infrastructure like rooftop gardens and tree-lined streets to help cool down overheated urban zones. In the agricultural sector, farmers are moving toward more resilient crops that can survive with less water, while also employing advanced irrigation methods that reduce waste. And in regions where rainfall has become unpredictable, water conservation is no longer optional. It's a daily necessity. People are learning to live with less and to plan for dry spells as a routine part of life. Even in these harsh environments, there's still a certain kind of beauty. Cracked soil creates stunning natural patterns, grasses sway in dry breezes, and lone trees cast dramatic silhouettes beneath vast, cloudless skies. Heat waves, while oppressive, can also bring visual marvels. Sunsets that glow like molten gold as sunlight filters through hazy, heated air. And when the first rain finally falls after a long, dry spell, it feels like more than a change in weather. It feels like a return, a reunion with life-giving moisture. So, when the heat bears down and the wind lies still, take a moment to notice the quiet transformation at play. This is weather without thunder or lightning, without hail or storm surge. It's the kind that molds the landscape in silence and etches its memory deep into the earth. Heat and drought may not roar like hurricanes or flash like lightning, but their impact is no less profound. They write their story in dry riverbeds and sun-baked hills, in the scent of hot dust and the stillness of parched afternoons. And they remind us that even the gentlest forms of weather, those that don't arrive with a crash, still carry the power to change everything. Then there are weather phenomena that enchant us rather than overwhelm. These quiet wonders emerge when storms subside, or when light and moisture align just right. They are nature's optical poetry, subtle, fleeting, and breathtaking, where you might catch sight of the entire circle suspended in the air. A primary rainbow always forms at an angle of roughly 42 degrees from the direction opposite the sun. That means the sun must be behind you, and the rain or mist in front. Because of this alignment, you can never walk up to a rainbow. It shifts with your movement. The one you see isn't the exact same one someone standing nearby sees. Each person perceives their own rainbow, created by the light that reaches their eyes alone. It's like a signature made of sunlight. Occasionally, you'll spot a second, dimmer arc beyond the first. This is a double rainbow. It happens when light bounces twice inside each raindrop before leaving. The extra reflection causes the outer rainbow to appear higher in the sky, and with its colors flipped, red on the inside, violet on the outer edge. Between these two arcs, you might notice a darker strip called Alexander's Band, named for the ancient Greek thinker who first described it. But rain isn't the only thing light can dance through. Enter the realm of halos, sundogs, and light pillars, dazzling effects created not by raindrops but by ice crystals drifting in the upper atmosphere. These ice crystals are usually found in cirrostratus clouds that hover 5 to 8 miles above Earth. A halo is a luminous ring, sometimes tinged with subtle rainbow hues, that surrounds the sun or moon. It forms when light passes through hexagon-shaped ice crystals and bends at an angle of 22 degrees, creating a ghostly glow like a floating crown. Halos can appear any time of year, but they're most common during cold seasons when the upper air holds more ice. Sundogs, also known by their poetic name, parhelia, are glowing spots that show up to the left and right of the sun, often inside the halo. They resemble mini-suns and shine especially bright when the sun is low on the horizon. Like halos, sundogs are caused by sunlight refracting through ice crystals, but only when the crystals are perfectly aligned like tiny mirrors drifting in the sky. Then there are light pillars, vertical shafts of light that seem to rise straight into the heavens, visible not just from the sun but also from streetlights or moonlight. These ethereal columns are created when flat, plate-like ice crystals slowly descend through calm air, catching and reflecting light upward in a straight beam. They seem futuristic but require nothing more than the right atmosphere and a chill in the air. One of the more delicate atmospheric effects is the glory. Despite its name, it's subtle, a set of soft, colorful rings that appear around your shadow when cast onto a cloud or fog bank. Best seen from airplanes, glories form as sunlight is backscattered by tiny water droplets. Related to glories are coronas, compact rings of color that encircle the sun or moon when light diffracts through fine mist or thin cloud layers, producing a soft pearly glow that feels almost magical. And then, of course, there's the sky's most theatrical performance, crepuscular rays, often nicknamed God rays. These striking beams of sunlight seem to burst outward from the sun, most commonly visible at sunrise or sunset when the sun hangs low and clouds scatter its light. Though they appear to spread dramatically across the sky, this is a trick of perspective, much like how parallel railroad tracks appear to meet on the horizon. These rays form when sunlight pierces through breaks in cloud cover or between mountains, illuminating dust, moisture, or pollen in the atmosphere. The sharp contrast between light and shadow creates an illusion of glowing fingers reaching from the heavens. No wonder they've long been seen as spiritual or magical. Now, let's step deeper into twilight to explore another rare optical event, the green flash. This fleeting phenomenon takes place just before sunrise or moments after sunset, when the sun is nearly below the horizon. For a brief instant, often less than a second, the upper rim of the sun may flash green. This is due to the Earth's atmosphere acting like a prism, bending sunlight as it passes through. Since green and blue light bend more than red and orange, under just the right conditions, the last visible edge of sunlight can glow emerald. It's rare, can you'll miss it rare, but sailors and skywatchers have treasured this moment for generations. Then there are lunar rainbows or moonbows, a quieter, dimmer sibling to the rainbow. These arcs are created not by sunlight but by moonlight reflecting off rain or mist. Because moonlight is far weaker than sunlight, moonbows are typically white or silver to the naked eye. However, with a long camera exposure, their muted colors can emerge. For a moonbow to appear, you need a nearly full moon, rain in the distance, and the moon positioned low behind you. It's a delicate alignment, but when it all comes together, the result is otherworldly. All of these displays, rays, flashes, halos, and bows, are vivid reminders of how light constantly interacts with our atmosphere. The sky is always performing, even if we don't always notice. When moisture, light, and timing align just right, the air transforms into a living canvas of color and contrast. You don't need a telescope or high-tech gear to enjoy these effects, just an open sky, a curious mind, and the patience to watch. Whether it's a rainbow soaring after summer rain, a halo crowning the winter sun, or a glory circling your plane's shadow, each of these phenomena is like a soft message from above. Nature doesn't only speak through thunder or downpour, it whispers through light and shadow, through shimmer and curve. Weather shapes our world, but light colors it, turning our skies into galleries of silent beauty. And just as weather can differ block by block, it also reveals its splendor across the globe, shaped by land, ocean, elevation, and wind. Nowhere are monsoons more influential than in South Asia, especially across India, Bangladesh, Nepal, and neighboring countries. During summer, the landmass heats up much faster than the surrounding ocean, forming a massive low-pressure area over the Indian subcontinent. In response, moist air from the Indian Ocean surges inland to fill this gap. As it collides with the towering Himalayan mountains, the air is forced upward, cooling and condensing into towering rain clouds. The result? Weeks, sometimes months, of continuous rainfall. These rains are crucial to the region's survival, replenishing rivers, recharging groundwater, and watering vital crops. Yet, despite its life-sustaining role, the monsoon can also be destructive, bringing deadly floods, triggering landslides, and grinding transport systems to a halt. Still, after the searing, bone-dry pre-monsoon heat, millions greet it with open arms as a long-awaited relief. Farther east, countries like Thailand, Vietnam, and the Philippines also fall under the influence of seasonal monsoons, though the timing and intensity vary. In East Asia, for example, the monsoon results in hot, wet summers and cold, dry winters, shaping everything from rice farming schedules to how cities are built. Meanwhile, in northern Australia, the summer monsoon, called the wet, brings a rush of tropical downpours and fierce thunderstorms between December and March. Thunder cracks through the humid skies, lightning dances across the horizon, and the air feels thick with moisture and drama. Now, let's pivot toward the deserts, lands of extremes where weather is anything but quiet. Though often portrayed as barren wastelands, deserts are alive with powerful atmospheric events. In the Sahara, the planet's largest hot desert, temperatures by day can surge beyond 120 degrees Fahrenheit, only to plunge 40 or 50 degrees after sunset. That wild swing is due to the lack of moisture and vegetation. Without water in the air or soil to trap warmth, heat radiates back into space quickly after dark. Dust storms are another signature desert event. In North Africa and the Middle East, they're often called haboobs, massive, fast-moving walls of dust and sand triggered when cold air from thunderstorms slams into dry ground, lifting particles into the atmosphere. These rolling clouds can stretch for miles, wipe out visibility, block out sunlight, and blanket everything in fine grit. Similar spectacles occur in Australia, where red dust can be swept clear across the continent, and in the American Southwest, where summer thunderstorms stir up dust storms that tear across desert highways. In stark contrast to these fiery deserts are Earth's coldest zones, the Arctic and Antarctic. Here, weather dances with ice, wind, and wild light cycles. Winters plunge into round-the-clock darkness and punishing cold, while summers flip the switch to endless daylight and melting permafrost. One hallmark of polar weather is the katabatic wind, a chilling flow of dense, cold air descending from icy plateaus. In Antarctica, these winds can roar with hurricane strength, blowing snow sideways and causing whiteout conditions. Despite all the ice, both polar regions are technically classified as deserts because they receive so little precipitation. Much of the snow covering the surface today is ancient, having fallen thousands of years ago and never melting. New snowfall arrives gently, almost invisibly, as tiny glittering crystals. Now let's journey to the equator, where the weather bursts with energy and color. Tropical zones such as the Amazon, Congo Basin, and parts of Southeast Asia are home to rainforests that thrive on nearly constant rainfall. Here, convectional rain dominates. By midday, intense sunlight heats the ground, causing warm air to rise rapidly. This moisture-laden air cools and condenses into thick, towering cumulonimbus clouds, resulting in afternoon thunderstorms nearly every day. These storms are short but fierce, delivering life-giving rain that sustains lush forests teeming with biodiversity. This consistent rhythm of warmth and moisture fosters dense canopies, complex ecosystems, and the ceaseless soundtrack of wildlife. Just beyond the tropics lie the savanna regions, where rainfall is not year-round but highly seasonal. Here, long dry spells alternate with intense rainy periods, shaping the timing of plant growth, animal migrations, and even cultural traditions. In the savannas, where expansive grasses stretch out and grazing herds roam freely, the timing of rainfall is vital. If the rains arrive too early or too late, the entire balance of the ecosystem can collapse, disrupting plant growth, animal migrations, and predator-prey relationships. Meanwhile, island nations, particularly in the vast Pacific, deal with distinct weather systems shaped by trade winds, ocean currents, and powerful tropical cyclones. One of the most influential of these global weather forces is the El Niño Southern Oscillation, or INSO. During El Niño phases, warm ocean waters shift eastward across the Pacific, upsetting rainfall patterns across multiple continents. from drenching parts of South America to drying out regions in Australia, Southeast Asia, and even Eastern Africa. Conversely, La Niña brings a different pattern: cooler Pacific waters, shifting wind and rainfall patterns in the opposite direction, and often intensifying hurricanes in the Atlantic. Ocean currents like the Gulf Stream in the Atlantic and the Kuroshio Current in the Pacific act as planetary conveyor belts for heat. These currents move warm water from the equator toward the poles, regulating global climates. For example, the Gulf Stream carries warm water northward, making the United Kingdom's winters surprisingly mild despite its high latitude. Without these currents, many coastal regions would be far colder or more extreme in temperature than they are today. In highland areas, such as the Andes, the Himalayas, or the Rocky Mountains, elevation becomes a key factor. As moist air ascends mountain slopes, it cools and condenses, leading to orographic precipitation, rainfall and snowfall concentrated on the windward side. Once the air passes over the peak, it descends on the leeward side, becoming warmer and drier, often creating rain shadow deserts. That's why Chile's Atacama Desert, sitting just west of the Andes, is one of the driest places on Earth. Along coastlines, the ocean's nearby presence tempers the climate, reducing temperature extremes. Coastal regions tend to enjoy mild winters and cooler summers due to the water's ability to store and slowly release heat. In contrast, areas located deep inland experience dramatic seasonal changes. Central Asia, for instance, can swing from scorching summer highs to bitterly cold winters. Yet up in coastal Norway, even at far northern latitudes, the Gulf Stream moderates the climate, allowing for comparatively warm winters and cooler summers. Microclimates add another layer of complexity to this global picture. A shaded valley may retain cool moisture even when sun-baked ridges nearby feel like ovens. In urban environments, heat islands form where glass buildings and pavement trap warmth, making one city block feel degrees hotter than a nearby shaded park. Even vineyards growing on opposite sides of a hill may produce completely different types of grapes because of slight changes in sun exposure, wind direction, or soil drainage. Despite all this variety, the fundamentals of weather remain remarkably consistent. The same laws apply whether you're standing in the driest desert or the wettest rainforest. Warm air rises, moisture condenses, and air flows from areas of high pressure to low pressure. These are the basic mechanics driving the entire system. What changes are the local conditions, the interplay of land, sea, altitude, and atmosphere, that produce everything from gentle breezes to violent storms. So, wherever you are in the world, watching lightning fork across a humid equatorial sky, sheltering during a sandstorm in a desert canyon, or standing quietly as snowflakes gather on frozen tundra, you're witnessing just one variation of a single, interconnected atmospheric story. It's a story of sunlight and shadow, wind and moisture, movement and stillness, all choreographed on a planetary scale. We've now explored the many faces of weather, but how do we know what's coming next? How can meteorologists predict whether a thunderstorm is brewing or if the skies will be clear enough tomorrow to dry your clothes on a line? Weather forecasting may seem like a blend of art and guesswork, but it's a precise science rooted in data, physics, and careful, continuous observation. Weather forecasting is among the most intricate and essential endeavors humans undertake. At its core lies a deceptively simple goal: to observe the present in order to foresee the future. But to accurately predict what's ahead, meteorologists must first build a complete and current picture of what's happening, not just locally, but globally. That's because the atmosphere is a vast, interconnected system. A thunderstorm developing over Texas today could be linked to a larger weather system that will influence conditions in New York tomorrow or even ripple across the Atlantic to affect Europe days later. To track all this, meteorologists rely on an extensive web of observation tools. On the ground, thousands of weather stations are spread across the globe. These stations measure key variables like temperature, humidity, wind speed and direction, atmospheric pressure, and precipitation levels. Some of these stations are fully automated, quietly collecting and transmitting data every few minutes, while others are operated and maintained by trained personnel. All of this information is fed into global databases, creating a snapshot of the Earth's current weather in near real time. But the story doesn't stop at the surface. To understand what's going on higher up in the atmosphere, meteorologists launch specialized weather balloons known as radiosondes. Released from numerous locations around the world, usually twice daily, these balloons ascend to heights of about 20 miles before eventually bursting. Attached to each balloon is a small device that records atmospheric data throughout the journey, measuring how temperature, pressure, humidity, and wind shift with altitude. This vertical profile is crucial in assessing the stability of the atmosphere and identifying the potential for storms, turbulence, or calm weather layers. The true game-changer in weather prediction, however, came with the introduction of satellites. Orbiting hundreds to thousands of miles above Earth, weather satellites provide a constant stream of images and data that help meteorologists monitor the planet's atmosphere from a unique vantage point. There are two primary types: geostationary satellites, which hover over a fixed point on Earth and deliver continuous coverage of that region, and polar orbiting satellites, which travel around the globe from pole to pole, capturing high-resolution data as they sweep over different areas. These satellites allow scientists to observe cloud patterns, monitor sea surface temperatures, track the birth and evolution of hurricanes, and even assess atmospheric moisture. They're also invaluable in spotting natural hazards like volcanic ash clouds, wildfires, or extensive snow cover. The dramatic, swirling cloud animations and vivid weather maps you often see on TV or online. Those are largely constructed from satellite imagery. Closer to Earth, another key tool takes a different approach: radar. While satellites look down from above, weather radars scan horizontally across the land. A radar system emits pulses of radio waves that bounce off particles in the atmosphere, typically raindrops, snowflakes, or hail. By analyzing how long it takes for the signal to return and how much energy it retains, radars can pinpoint the location, intensity, and movement of precipitation. This technology is especially useful for short-term, or nowcasting, forecasts, like determining whether a thunderstorm will pass over your neighborhood in the next hour. Combined with satellite views, radar offers a dynamic, three-dimensional perspective on weather systems in motion. Together, these tools allow meteorologists to monitor the atmosphere in real time and anticipate its next moves with ever-increasing accuracy. To reveal where precipitation is occurring, how intense it is, and how quickly it's moving. A specialized type, Doppler radar, goes even further by detecting movement within storm cells, making it an essential tool for spotting rotating systems that may lead to tornadoes. All this data, billions of individual readings gathered each day, feeds into massive computational models. These numerical weather models are complex software programs built to simulate atmospheric behavior based on physics. They divide Earth's atmosphere into a vast 3D grid, with each cell representing a tiny volume of air. Within each cell, equations estimate how temperature, pressure, humidity, and wind will evolve in response to their neighbors. This process is intensely detailed and requires vast computing power. Supercomputers handle these intricate simulations, solving equations that describe atmospheric motion, heat transfer, moisture behavior, cloud development, and more. There are several prominent weather models in use globally, including the US-based Global Forecast System, GFS, Europe's ECMWF, European Centre for Medium-Range Weather Forecasts, and the UK's Met Office model. Each one has unique algorithms, strengths, and limitations. Despite the enormous complexity of these models, forecasts can't be perfect. That's because the atmosphere behaves like a chaotic system, where tiny changes in initial conditions can lead to dramatically different results later on. This is the basis of what's known as the butterfly effect, the idea that a small, seemingly insignificant action in one part of the world could set off a chain of events far away. In practical terms, this means even slight errors in measurement or data can snowball into major forecast differences as time progresses. To address this, meteorologists turn to ensemble forecasting. Rather than running a single simulation, they run the model multiple times, each time tweaking the starting data slightly. This generates a spread of possible scenarios. Analysts then look at this range to determine the most probable outcome. If all simulations point to a similar result, the forecast carries higher certainty. If they vary significantly, it indicates a more volatile or uncertain weather event. But even with advanced algorithms, human expertise remains indispensable. Meteorologists don't just rely on raw model output, they interpret it, compare competing predictions, and apply local knowledge. A computer might not understand how a coastal cliff funnels wind or how urban structures affect heat retention, but a trained forecaster does. That's where professional judgment bridges the gap between automated calculation and real-world nuance. Forecasting has come a long way. Today's 3-day outlook is as reliable as a 1-day prediction was 4 decades ago. 5-day forecasts are now fairly solid, and even 10-day projections, while less precise, can highlight general trends. Still, the farther you extend into the future, the less specific the forecast becomes, as small initial uncertainties multiply over time. Short-term predictions, or nowcasting, are especially vital for fast-developing systems like thunderstorms or tornadoes. These forecasts rely on real-time radar, ground observations, and rapidly updating models, some refreshing as often as every 15 minutes. This data enables meteorologists to issue critical watches and warnings, potentially saving lives during severe weather events. There's also a shift toward probabilistic forecasting. Instead of saying, "It will rain tomorrow," you might hear, "There's a 70% chance of rain." This better reflects the nature of forecasting, not a promise, but a likelihood based on current conditions. Probabilities empower individuals to make informed choices, whether to bring an umbrella or delay a planned event. Weather predictions impact far more than daily routines. Aviation depends on accurate forecasts to schedule flight paths and avoid turbulence. Farmers rely on rainfall and frost outlooks to safeguard crops. Utilities use temperature projections to balance energy loads, while emergency responders prepare for hurricanes, blizzards, and wildfires based on forecasts. Forecasting is also evolving thanks to machine learning and artificial intelligence. These technologies can parse enormous data sets, uncover patterns, and boost model reliability. While they won't replace traditional models yet, they are becoming critical tools for refining results and shortening response times. And finally, the everyday observer now play a part. With modern apps and smartphones, millions of users contribute to crowdsourced platforms, reporting rain, snow, temperature, and sky conditions. These contributions help cover observation gaps, especially in remote or under-monitored regions, making community engagement a key asset in the global weather system. Filling the observational gaps between official weather stations, offering more precise views of ground-level changes. So the next time you glance at your weather app and see a forecast calling for 72 degrees Fahrenheit with a 20% chance of rain, consider everything behind that tiny icon: hundreds of orbiting satellites scanning Earth's surface, high-altitude balloons collecting critical readings, supercomputers crunching billions of numbers, seasoned meteorologists analyzing patterns, and maybe even someone in their yard noticing a shift in the breeze. It's an extraordinary collaboration, a global alliance dedicated to understanding the sky. While we may not command the elements, our capacity to anticipate their behavior has never been more advanced. Weather has always been a chameleon, sometimes calm, other times destructive, forever shifting. Yet over the past 100 years, and especially in recent decades, we've detected something profound. Weather itself is evolving. These changes aren't just seasonal quirks, they're part of a long-term transformation. At the core of this shift is a force frequently in the headlines: climate change. To grasp how climate change affects weather, we first need to separate two often confused terms: climate and weather. Imagine weather as the atmosphere's mood. It changes daily. Is it cloudy today? Is the wind blowing gently, or is it humid and warm? That's weather, short-lived and localized. Climate, on the other hand, is like the atmosphere's character. It represents long-term patterns, typically tracked over at least 3 decades. Climate tells us what's normal for a region, how much rainfall occurs each spring, how cold winters get, and how frequently storms appear. Throughout Earth's past, the climate has never remained completely still. Our planet has toggled between ice ages and milder periods due to natural causes, variations in the planet's orbit, volcanic eruptions, fluctuations in solar energy, and more. But the pace and nature of today's warming stand apart. The shifts we now observe are occurring rapidly, and they're largely driven by human influence. Since the late 1800s, Earth's average temperature has climbed by more than 2 degrees Fahrenheit. That may seem modest, but for a planetary climate system, it's significant. The main cause is the greenhouse effect, a natural mechanism where gases trap solar heat in the atmosphere, keeping the planet warm enough to sustain life. The primary contributors include carbon dioxide, methane, nitrous oxide, and water vapor. While all play a role, carbon dioxide has taken center stage in our current climate narrative. Carbon dioxide is released primarily through the combustion of fossil fuels, coal, oil, and gas, and through land use changes like deforestation, which reduces the number of trees that would otherwise absorb CO2. As greenhouse gas levels rise, more thermal energy is retained within the atmosphere, pushing global temperatures upward. And that warming affects much more than just summer heat. It disrupts weather systems worldwide. Let's revisit heat waves, which we touched on earlier. These prolonged periods of extreme warmth are growing increasingly frequent, severe, and long-lasting in many parts of the globe. What once occurred once in 2 decades can now happen every few years, or even annually. Cities, burdened with concrete and asphalt, amplify this warming through the urban heat island effect, intensifying the heat's impact. Interestingly, nighttime temperatures are climbing faster than daytime highs. That may seem minor, but it matters greatly. Warmer nights prevent natural cooling, raising health risks and stressing crops and livestock that rely on nightly recovery from daytime extremes. Rainfall patterns are also undergoing major shifts. Some regions are experiencing more frequent and heavier rains, while others endure prolonged dryness. That's because warmer air has the capacity to hold more water, about 4% more for each 1 degree Fahrenheit rise in temperature. When this moisture is released, it often comes as intense, concentrated downpours. We're already witnessing more powerful and erratic rainfall events, with storms that can drop several inches of rain in just a few hours, overwhelming drainage systems and causing flash floods. These extremes, whether it's parched soil or flooded streets, signal a climate system under stress, reshaping how we prepare for and respond to weather in every part of the world. That exceeds storm drains' capacity, inundate roadways, and erode topsoil. But having more moisture suspended in the atmosphere doesn't ensure equal rainfall for all. Some places are trending drier, especially regions historically vulnerable to arid conditions. Prolonged dry periods, coupled with rising heat, are drying out land, depleting rivers, and placing stress on local ecosystems. In areas like the American Southwest, Southern Europe, and portions of Africa, droughts are not only more common, they're more intense. This growing polarization, where the wet get wetter and the dry become drier, is a defining trait of climate change. It's not just about a warming trend, it's about a total rearrangement of the climate system. Storms are shifting too. As ocean temperatures rise, they feed more energy into tropical weather systems, making hurricanes, typhoons, and cyclones stronger. Research suggests that while the overall quantity of these storms each year hasn't spiked significantly, their power has. High-intensity storms, classified as Category 4 or 5, are becoming more frequent. These massive systems also carry more water, leading to heavier rainfall when they hit land. Hurricanes like Harvey in 2017 and Florence in 2018 dumped record-setting rainfall, causing devastating floods far inland, well beyond where people typically expect storm damage. In colder climates, winter weather is also evolving. A warmer world doesn't eliminate snow. It can, paradoxically, increase snowfall in some regions due to higher atmospheric moisture. However, the pattern of winter is changing. Snow arrives later, melts sooner, and snowpack, the seasonal storage of water in mountain regions, is steadily shrinking. This affects ecosystems, agriculture, and water supply systems that depend on gradual snowmelt. Another significant shift involves the jet stream, the high-altitude wind current that steers weather systems around the globe. As the Arctic experiences accelerated warming, a process known as Arctic amplification, the temperature gap between the poles and the equator narrows. This weakens the jet stream, making it more erratic and slower. A less stable jet stream can cause weather systems to stall, keeping a storm or heat wave locked in place for days. These stalled systems have contributed to numerous extreme events in recent years, including long-lasting heat waves in Europe and multi-day floods across the US. Then there's rising sea levels, not a weather phenomenon per se, but one that changes how we experience weather in coastal zones. Melting glaciers and expanding ocean waters have raised global sea levels by approximately 8 inches since the late 19th century. This may seem small, but it dramatically amplifies the reach and impact of storm surges and tidal floods. Storms that once only soaked beaches now inundate city streets and waterfront neighborhoods, putting more communities at risk. Climate change is also influencing wildfires, not by starting them directly, but by setting the stage for them to ignite and spread. Hotter air, drier landscapes, earlier snowmelt, and longer dry spells extend fire seasons. More convective storms may increase lightning, nature's matchstick, and when fires do begin, high winds and flammable vegetation help them expand rapidly. As a result, we're seeing more severe, frequent, and fast-moving wildfires in regions like California, Australia, and even the Siberian tundra. It's important to remember that not every weather event is caused by climate change. The weather will always fluctuate, cold snaps will still occur, there will be rainy weeks and calm seasons. But what scientists now focus on is how climate change alters the likelihood and intensity of these events. This field, known as attribution science, investigates how rising background temperatures and shifting conditions increase the odds or strength of a particular storm, drought, or heat wave. So what can humanity do in response? First, it's vital to understand that the future isn't set in stone. While some warming is already unavoidable due to past emissions, the degree of future change depends on decisions made today. Reducing emissions of greenhouse gases, transitioning to clean energy, increasing energy efficiency, conserving forests, and adopting sustainable agricultural and land use practices, all these actions can slow the rate of change. Adapting is equally essential. Communities worldwide are investing in smarter infrastructure that can handle torrential rains, planting urban trees to lower city temperatures, and revising building codes to withstand intense storms. Farmers are testing drought-hardy crops, and cities are identifying flood-prone areas to better prepare for future challenges. And constructing coastal defenses while individuals, people like you, are learning how to stay safe in intense heat, conserve water, and minimize their carbon emissions. Even seemingly minor efforts matter, and when multiplied across millions of people, they become transformative. Choosing to walk instead of drive, switching off lights when not in use, or advocating for environmental policies, each action contributes, like individual drops filling a bucket. Weather remains, as ever, unpredictable, mesmerizing, sometimes volatile, but the stage on which it performs is shifting. The limits have moved. The consequences have grown. And we, humans, are not just spectators, we're part of the story. So next time the clouds roll in out of nowhere, the heat wave lingers longer than expected, or the rainfall feels heavier than normal, pause for a moment. You're not just experiencing the weather, you're witnessing a scene from a broader tale. A tale of a world in transformation, where every gust of wind and every sudden storm tells part of a global narrative. One that continues to evolve, shaped by nature and by us. And so we've wandered through tempests and sunshine, drifted alongside mist, and stood still as snow blanketed the ground. We've followed flashes across night skies, felt the hush of deserts at dusk, and learned how invisible forces choreograph weather across continents. From soft clouds to powerful hurricanes, from how sunlight bends through raindrops to how wind finds its path, we've uncovered some of the secrets behind our planet's ever-shifting atmosphere. Weather is far more than a background condition. It's a dynamic dialogue between land, ocean, and sky, a language formed by heat, vapor, and motion. It's written in shifting cloudscapes, spoken through thunderclaps and breezes. It carves valleys, nourishes crops, brings challenges and comfort, urgency and awe. Even with all our sensors, models, and satellites, weather continues to defy our full grasp. Just when we think we understand it, it surprises us. And tonight, wherever you lay your head, the skies above remain in motion. Winds sweep quietly over ridgelines. Rain gathers in distant treetops. Somewhere, in some quiet, frigid place, a single snowflake starts to crystallize. There's something soothing in that continuity, the knowledge that the sky is always alive, always flowing, always shifting. It doesn't sleep, it transforms, quietly carrying on its timeless rhythm. And before we conclude, I want to ask, where are you joining me from? Is it late at night, maybe just past midnight? Or the early hours of the morning? Perhaps it's a calm afternoon with the blinds drawn and the world hushed around you. Wherever you are, whenever you've tuned in, thank you. Thank you for coming along on this exploration through the weather's hidden wonders and science. If this journey left you feeling calm, curious, or simply fascinated by the beauty of our skies, I'd love for you to leave a like or consider subscribing to The Sleepy Scientist. It helps others find this peaceful space too, and it truly means a lot. Now rest easy. Let your thoughts wander like drifting clouds. And may your dreams be as soft as mist and as luminous as the sky after a cleansing rain. Shifting conditions increase the odds or strength of a particular storm, drought, or heat wave. So what can humanity do in response? First, it's vital to understand that the future isn't set in stone. While some warming is already unavoidable due to past emissions, the degree of future change depends on decisions made today. Reducing emissions of greenhouse gases, transitioning to clean energy, increasing energy efficiency, conserving forests, and adopting sustainable agricultural and land use practices, all these actions can slow the rate of change. Adapting is equally essential. Communities worldwide are investing in smarter infrastructure that can handle torrential rains, planting urban trees to lower city temperatures, and revising building codes to withstand intense storms. Farmers are testing drought-hardy crops, and cities are identifying flood-prone areas to better prepare for future challenges. And constructing coastal defenses while individuals, people like you, are learning how to stay safe in intense heat, conserve water, and minimize their carbon emissions. Even seemingly minor efforts matter, and when multiplied across millions of people, they become transformative. Choosing to walk instead of drive, switching off lights when not in use, or advocating for environmental policies, each action contributes, like individual drops filling a bucket. Weather remains, as ever, unpredictable, mesmerizing, sometimes volatile, but the stage on which it performs is shifting. The limits have moved. The consequences have grown. And we, humans, are not just spectators, we're part of the story. So next time the clouds roll in out of nowhere, the heat wave lingers longer than expected, or the rainfall feels heavier than normal, pause for a moment. You're not just experiencing the weather, you're witnessing a scene from a broader tale. A tale of a world in transformation, where every gust of wind and every sudden storm tells part of a global narrative. One that continues to evolve, shaped by nature and by us. And so we've wandered through tempests and sunshine, drifted alongside mist, and stood still as snow blanketed the ground. We've followed flashes across night skies, felt the hush of deserts at dusk, and learned how invisible forces choreograph weather across continents. From soft clouds to powerful hurricanes, from how sunlight bends through raindrops to how wind finds its path, we've uncovered some of the secrets behind our planet's ever-shifting atmosphere. Weather is far more than a background condition. It's a dynamic dialogue between land, ocean, and sky, a language formed by heat, vapor, and motion. It's written in shifting cloudscapes, spoken through thunderclaps and breezes. It carves valleys, nourishes crops, brings challenges and comfort, urgency and awe. Even with all our sensors, models, and satellites, weather continues to defy our full grasp. Just when we think we understand it, it surprises us. And tonight, wherever you lay your head, the skies above remain in motion. Winds sweep quietly over ridgelines. Rain gathers in distant treetops. Somewhere, in some quiet, frigid place, a single snowflake starts to crystallize. There's something soothing in that continuity, the knowledge that the sky is always alive, always flowing, always shifting. It doesn't sleep, it transforms, quietly carrying on its timeless rhythm. And before we conclude, I want to ask, where are you joining me from? Is it late at night, maybe just past midnight? Or the early hours of the morning? Perhaps it's a calm afternoon with the blinds drawn and the world hushed around you. Wherever you are, whenever you've tuned in, thank you. Thank you for coming along on this exploration through the weather's hidden wonders and science. If this journey left you feeling calm, curious, or simply fascinated by the beauty of our skies, I'd love for you to leave a like or consider subscribing to The Sleepy Scientist. It helps others find this peaceful space too, and it truly means a lot. Now rest easy. Let your thoughts wander like drifting clouds. And may your dreams be as soft as mist and as luminous as the sky after a cleansing rain. Even with all our sensors, models, and satellites, weather continues to defy our full grasp. Just when we think we understand it, it surprises us. And tonight, wherever you lay your head, the skies above remain in motion. Winds sweep quietly over ridgelines. Rain gathers in distant treetops. Somewhere, in some quiet, frigid place, a single snowflake starts to crystallize. There's something soothing in that continuity, the knowledge that the sky is always alive, always flowing, always shifting. It doesn't sleep, it transforms, quietly carrying on its timeless rhythm. And before we conclude, I want to ask, where are you joining me from? Is it late at night, maybe just past midnight? Or the early hours of the morning? Perhaps it's a calm afternoon with the blinds drawn and the world hushed around you. Wherever you are, whenever you've tuned in, thank you. Thank you for coming along on this exploration through the weather's hidden wonders and science. If this journey left you feeling calm, curious, or simply fascinated by the beauty of our skies, I'd love for you to leave a like or consider subscribing to The Sleepy Scientist. It helps others find this peaceful space too, and it truly means a lot. Now rest easy. Let your thoughts wander like drifting clouds. And may your dreams be as soft as mist and as luminous as the sky after a cleansing rain.